Thank you, man. Hope you are well. Great day. So today we're going to be discussing something interesting. Today we want to discuss something about proofs in mathematics. There is a certain topic that if you get your third year in university maths, it's called analysis. It's going to be built up through the use of proofs. So maybe you want to prove why 1 added to 1 will give you 2. You want to prove maybe why a certain summation is equal to a factor of 1 minus r over 1 minus r to some power n. So those are the particular kinds of conversations that we want to have today. I want to be very clear with you on the beauty of mathematics, pure mathematics to be quite frank. If you just try and understand how mathematics works, it's a bunch of defined signs that try to explain certain things that are discovered. That is to say, in the wise words of Neil deGrasse Tyson, mathematics is not purely invented, but you had to invent something in order to explain something that you discovered. So at the end of the day, the actual goal of pure mathematics is in and of it oneself to help you understand how mathematics behaves, so that at the end of the day you are generally able to take your degree and probably foster some form of meaningful correlation to how mathematics is formed. Good context there, I think you would agree with me. But let's get into proofs. Just 2 types of proofs I want to focus on today. Proof by the principle of mathematical induction and proof by contradiction. Let's start off with PMI, or the principle of mathematical induction. It's an interesting, a beautiful method of proving statements in mathematics that will lead you to certain revelations that you never thought of. It assumes about 6 steps, and I want you to pay attention. The first step is writing a statement P of n for whatever statement you want to prove. Maybe it's the integral of any polynomial x to the degree of n is supposed to give you an integral of x to the n plus 1 over n plus 1 plus c. So you want to define a statement that is explained in the form of the letter n. Then the next step that you obviously want to take is a step that assumes, or at least tries to prove that statement in a condition whereby n is the smallest value that it can assume. Books will classically tell you that you are proving when n is equal to 1. But the vast majority of cases, there are some problems, especially in series summation, that will become indeterminate or undefined if you ever try to prove them at n is equal to 1 or at n is equal to 2. So that's why for this particular example, I'll just say the smallest value that n can assume at a given time. From there you go to the third stage, which is the loveliest stage, assuming that the statement is true for n is equal to some k. Understand now that when you say n is equal to some k, there's an attachment to the condition of k. In most cases, you just restrict k to the real number, to the natural number set rather than the real number set. So you restrict it to the counting whole numbers. That is 1, 2, 3, all the way up to infinity. So k is a number ideally between 1 and infinity. It's an element in the set of natural numbers. So you assume that the statement is true for n is equal to k based off the assumption, or based off the proof that you made that the statement is particularly true for n is equal to 1. The next step is where principle of mathematical induction becomes interesting. It says we write a statement for n is equal to k plus 1, where k plus 1 is the next term after the kth term. So when then you write that statement, the 5th stage, of course, is to write and prove that statement for n is equal to k plus 1. This is where principle of mathematical induction becomes kind of, what word can I use? The epitome of excellence in mathematics. because what you do at that stage is you take the proof that you achieved for n is equal to k, and you use it to progressively build up a proof that will otherwise give the statement that you aim to come out with for the proof of n is equal to k plus 1. So that k plus 1th term is otherwise the most important and integral part of that particular integral. So to that extent, you generally need to understand that by now you would have proved the statement if you are able to use n is equal to k to prove n is equal to k plus 1. The next thing that you then have to do in that particular instance is to conclude. The conclusion is the loveliest part of pure mathematics. That conclusion is in the great words of my maths teacher for A level. Therefore, since we have proved that the statement is true for n is equal to 1, n is equal to k, and n is equal to k plus 1, the statement is assumed to be true or to hold true for all subsequent values that n can assume at any given time. So that's it for today. I'm going to release a new video on proof using mathematical contradiction. Then of course I'm going to apply these into actual examples and workbooks that are sold on our PayHip store. Link is down in the bio. Be sure to subscribe. Thank you.